Okay, hello, people. Welcome to the second half of this presentation on relations. The midterms this Monday coming up. In week 10, this is the end of week 9. This presentation will span both week 9 and 10 because it's a very large presentation. It's over 120 slides long, and there's a midterm next week, so that's an hour taken out of these 2 weeks I have to compensate for. So, just maybe a little, we're ahead of the game here. We're ahead of schedule. So we'll just, slow down for this 2 weeks so you can recuperate from the midterm. Where did we leave off? We left off basically here. We left off. Oh, yes. Okay. So we left off with the cardinality of relations. Of course, the power set. How many binary relations are there on a set with n elements? Well, we know that the power set it gives you the set of it gives you all the subsets of a particular set. So A cross A is a set. It's a binary relation. It has n squared elements. We know that because of the power. That's the power. The power set of A cross A is n squared. And sorry, by the product rule, it's n squared. The cardinality of A twice by the product rule is n squared. And now the power set is 2 to the cardinality of the set that you're dealing with. That's n squared in this case. So the how many binary relations are there on a set with n elements? The answer is 2 to the n squared. Okay, and there's just a simple explanation or example. Okay, we remember I told you about the cardinality of relations, the number of reflexive relations, the number of symmetric relations. Just forget this stuff. We'll do enough of this with functions. That's the most important part. In all my years, I've never had to deal with the cardinality of relations, except for functions, of course. So that's the same for antisymmetric and symmetric. It's here for those that are interested. And irreflexive, reflexive. Now, let's talk about equivalence relations. An equivalence relation, well, don't forget that we had reflexive, symmetric, and transitive. Okay, those are the fundamental classes. And then, of course, there's classes of each one: reflexive, irreflexive, or not reflexive, and not anti-reflexive. So the symmetric, not symmetric, anti-symmetric, transitive, not transitive, anti-transitive. Those are I think, best ways of describing these things. Stick with my nomenclature. Stick with that slide back there that we dealt with before. There, this one, I think, remember this one. Make sure you memorize this and note that there is a lot of contradiction. I should say there's a lot of discrepancies with the nomenclature in the literature. Some textbooks will call anti-reflexive irreflexive. I mean, just stick with this. It's the best way. It's my way, and it's correct. So, okay, haven't done that. An equivalence relation in mathematics, we have worked with the equality relation. Okay, for example, let R be the relation on the set of integers defined as follows. For all A, B that are integers, A is a relation on B if and only if A equals B. Okay, we know this equality relation on integers has the following properties. Okay, for every integer A equals B, and so A is a relation on R. Sorry, A is a relation on A, so it's transitive. Reflexive. Okay, it's definitely reflexive. For A, B integers and A equals B, then B equals A. That is, if A is a relation on B, then the arc B to A is there, so that's symmetric. And of course, transitive, there's 3 nodes that we need, A, B, and C. So if you go from A to B and B to C, and you have to have A to C as well. And that's what we have written here. And so being all of these 3 is the requirements for an equivalence relation. Being transitive, symmetric, and reflexive. Make sure you know that. Equivalence relation. Reflexive, symmetric, and transitive. So a relation on a set A is called equivalence relation if it is a reflexive, symmetric, and transitive. Okay, this is out of your textbook. You can read this. 2 elements A and B are related by the equivalence relation. They're called equivalent. The notation A, squiggle or tilde, B is often used to denote that A and B are equivalent elements with respect to particular equivalence relation. Actually, it's the three lines that most people use. The three lines that this book, unfortunately, uses for logical implication or logical equivalence. I'm used to using the three lines, three bars. Yeah, let's just hold on just a second. Let me just check that out. Yeah, just yes, it's like I said. It's exactly like I said. I had to check it out, and with the textbook, and referred to Grimaldi as well. And then I asked ChatGPT, and the way I'm doing it and the way I'm describing it is correct. So I just have to make sure about that. So let's go back here. Like I said, I want you to use the double-headed arrow with two lines to be logical equivalence, rather than the three lines. Okay, so I want you to use this symbol for logical equivalence. Rosen uses this symbol. Now, this symbol is used also for congruences. But Rosen also uses this for logical equivalence. So there's a lot of confusion here. I want you to use this for logical implication or logical equivalence, and this for congruences, and that's it. Also, this is for an equivalence relation, although you can use this as well. Okay, this tilde is also very common, probably more common than that. But I'm used to the three lines. It's just make sure you understand these issues. Okay. So, okay, here, obviously, this is just saying the same thing. Okay. So we did the equals as an equivalence relation already. We've already done that. So equivalence relations can also be represented by digraphs. So we talked about digraphs already. Since they are a binary relation. Okay, a digraph is a binary relation on a set. For example, the digraph of the equivalence relation congruent mod 3 on this set of integers is as shown below. It consists of three connected components. So it is obviously reflexive, it is obviously symmetric as well, and transitive. Okay. What do we have here? We have the next one. It satisfies the same thing. It's de facto because there's only 2 points. It's not de facto. It's vacuously transitive, and this is vacuously transitive as well. Okay, we discovered we talked about what that is because there's no counterexample to prove that it is not transitive if you only have 2 points. Okay, here's one. The example here, let R be the relation on the set of integers such that A is a relation on B, if and only if A equals B or A equals minus B. In section 9.1, we showed that R is reflexive, symmetric, and transitive. It follows that R is an equivalence relation. Example 2, let R be the relation on a set of real numbers such that A is a relation on B, if and only if A minus B is an integer. Is R an equivalence relation? Let's look at that now. All right. Okay, why don't we do that? So, all right, I think we got it there. So because A minus B, A minus A equals 0, all right, is an integer for all real numbers A, A is a relation on A, okay, for all real numbers A. Real numbers, okay, there, real numbers. Hence, R is reflexive. Now suppose that A is a relation on B for some other. Okay. Then a minus b is an integer, clearly, because subtraction is closed under for integers. Subtraction is closed. That means if you subtract two, excuse me, integers, you're still in the set of integers. Okay. So b minus a is also an integer. Well, obviously then it follows it's symmetric, therefore symmetric. So it's reflexive, symmetric, and you know where this is headed. Now we're going to show that it's transitive. Okay. If A is a relation on B, and B is a relation on C, then A minus B and B minus C are integers. Therefore, A minus C equals A minus B plus B minus C is also an integer, clearly. Hence, you got it, we're done. Hence, R is an equivalent, R is transitive. Hence, R is transitive. Big conclusion, therefore, R is an equivalence relation. Okay. All right. It covers that. That's right there. And now I want to move things along here. This is just right out of your textbook. The next example has to do with modular arithmetic. Let me just get some paper here. One moment. I just can't separate pages anymore. Right. Okay. So the next example has to do with congruences. So I'm just going to walk you through this. I don't want to write the whole thing out. It'll take too much time. Congruence modulo m, okay? Let m be an integer with m greater than 1. Show that the relation R such that, or R equals in set builder notation, A integers A, B such that A is congruent to B modulo m. Just go right back to chapter 4. And that is an equivalence relation, okay? This one is a little more subtle. Let's just walk through it together. Okay, recall from section 4.1, of course, that A is going to be modulo M if and only if M divides A minus B. Go always straight to the definitions. They call that going to first principles. Okay, you do that in a physics class. That's what physics is all about, is going to first principles and dealing with all these. Same thing with mathematics. Just go to the definitions. Those are first principles. A is congruent to B modulo M seems like a really weird thing. We talked about that already. It's not normal arithmetic, but it is if you think about what it really means. Note that A minus A is 0, and that's clearly divisible by M. Excuse me. Because A equals 0 times M. Okay, hence A is congruent to A modulo M, so congruence. Modulo M is reflexive. Okay, you do the same thing with symmetry. Suppose again that A is congruent to B modulo M. Then A minus B is divisible by M, so A minus B equals some integer k times M. So it follows again here that B minus A equals minus k times M, so B is congruent to A modulo M. So you can see here, it's A to B and B to A, okay? And so next, suppose that A is congruent to B modulo M and B is congruent to C modulo M. So we need A, B, and C now. So clearly we need these two congruences. And you can see we just go to the same thing we just did before and show that it's transitive and that therefore it's an equivalence relation. You can do that. So total orders, let's talk about this. So not only do we have equivalence relations, but we have things called total orders. You're not going to be responsible for total orders, but I put it there so you understand what a partial order is. That's the big part of what we're doing here. Partial orders will haunt you throughout your academic undergraduate careers in computing science and mathematics. Total order can be thought of as intuitively as an order on the set of things under consideration. One follows another, stacked up like this. There is no, horizontal set of entities. Okay. You remember the power set of the integers a, b, or the elements a, b, c, and d. Let's have a look at that. Okay, let's see. Oh. Well, anyway, okay. Let me see if I can get myself a. I don't know how to do it with this machine here. I'm afraid of losing. Okay, here. This is what I wanted to show you. Okay, power set. Wikipedia has the best one. Okay, believe it or not, I can't stand Wikipedia, but this right here is not a total order because it just goes straight through down sequentially from one step to the next. Each step actually has a horizontal layer, a level. This is a partial order. A partial order is organized like this. A total order is where you start, where you just have the vertical part, not the two sides. Okay, so let's just remember that. All right, so we're back to this, and we want to go back to the slide. I'm glad I actually made that work. I'm very afraid to touch things because, sometimes I press the wrong button and it stops recording. That happened on 9A. You'll notice it just stopped abruptly because I pressed the wrong button. And I didn't want to continue on after all that at that time. So total orders are anti-symmetric, transitive, and they are so-called totality. A is less than or equal to B, or B is less than or equal to A. So you don't have to know this because you don't have to know what totality means. But just so you know, when we started talking about partial orders, you got to wonder where that came from. And it came from the idea of total orders. And like I said already, total orders visually are just, a sequence of steps, one after another, whereas a partial order is not. So for example, consider here an industrial renovation. So what do you do here? You remove asbestos. You know what that is? It's cancer-causing insulation from the past decades. Replace windows, paint walls, refinish floors, assign offices, move in office furniture. Some of these things can be done at the same time. These don't have to follow in this strict order. You can actually do these things, some of these processes at the same time. Okay, so that's the whole idea. Oh, God, went the wrong way. So what these things are the partial orders, the transitive, antisymmetric, and reflexive. So what was a total order? Antisymmetric, transitive, and the so-called totality. So forget about this. Forget the total order. This is all because I don't want to get into this particular type of relation. You get the idea by looking at it. So a partial order is transitive, not symmetric, which an equivalence relation would be, but antisymmetric. So, no parallel arcs. And reflexive, transitive, antisymmetric, and reflexive. That is what a partial order is. Okay. Excuse me. So let a relation R on a set A is called a partial ordering, a partial order. If it is reflexive, antisymmetric, or transitive, set A together with a partial ordering R is called a partially ordered set or a poset. The poset is denoted as S, R. So, for example, show that the inclusion of the inclusion relation. Okay, inclusion relation. This is the this set operation of subset. So inclusion, I would just call it the subset relation, is a partial ordering on the power set of a set A. So that we just actually looked at that when we went to the Wikipedia page. Solution: since every S set S is a subset of S by the definition of subset. Subset is reflexive, obviously. If S is subset on R and R is subset on S, then R equals S, which means the subset relation is antisymmetric. If we go back to the definition of antisymmetric, that is the definition. Okay, it is transitive. As R is a subset of S and S subset of T implies R is a subset of T. So no doubt about it. The symbol squiggle, like a very weird-looking less than or equal, is used to denote a posit. Okay, so the notation A less than kind of looking thing, B, I can't remember what this thing's called, is used to denote A is a posit on B, but A is not equal to B. Okay, so that it's just like the less than or equal to sign. Okay, it's just like that. Okay. All right. Go away. Well, okay, I've tried to figure out what that symbol's called. It doesn't have a, like a tilde-like name to it. It proceeds to. That's all it says here. You can see from ChatGPT here that it's called precedes or equal to. Precedes or equal to. So in other words, that's a partial order. That's all that is. Okay, so let's go back to this. So this precedes or equal to symbol is used for a posit. Okay, so that's what a partial order looks like. I forgot I had it in here. It's the classic way of looking at it. It's just not straight down in a sequence, but it has a horizontal structure to it as well as vertical. Problem set. Given the above on partial orders, answer the following questions. Prove that divisibility, this divisibility, is a partial order. A divides B means that A is a factor of B, i.e., on dividing B by A, no remainder results. Okay. Prove the following set is a partial order. A, B is precedes or equal to C, B, D, implies A, B is less than or equal to C, D for A, B, C, D integers ranging. Okay, so simple proof. Formalization of the proof is an optional exercise. Reflexivity, okay, A, B is precedes or equal to AB, since AB equals AB. Okay, so that's reflexive. Antisymmetric, AB is precedes or equal to CD, and CD precedes or equal to AB, since AB times CD and CD, is less than or equal to CD, and actually, I think, yes, that's fine. And CD is less than or equal to AB, so that takes care of the preceding part, and equals, which implies that AB equals CD, so that's antisymmetric. Transitive AB to CD, CD to EF implies AB to EF, okay, because it satisfies this set of inequalities. Okay, that's pretty simple. Now let's talk about Haas diagrams. Haas diagrams. So this is a way, as these diagrams can get really clumsy. I mean, imagine you got partial orders, you're reflexive. Every loop node has a loop. You've got parallel edges. You've got these transitive properties: A to B, B to C, A to C. I mean, it's just a big cluster. It turns out in the real life, these become very complicated. So partial orders, we just simplify it by first of all getting rid of all the loops. It's assumed if it's a partial order that there are loops here, so you just delete those loops. Just they're implicitly there, just to make the diagram look easier. The digraph. So what about the antisymmetric part? It's the transitive part. So we know that A goes to B and B goes to C means A goes to C. So we just get rid of that implicit in the transitivity, A to C. And so instead of this situation, we have this situation, because it's understood that this is a transitive relation. So in doing that, we can reduce this diagram to this diagram. So no loops, And also we've got 1 goes to 2, 2 goes to 4, and 1 goes to 4. We got rid of that. See, I don't have to go through the whole thing. 1 to 3, 3 to 12, 1 to 12. We've got rid of that too. All right, you get the idea. So here, look at how it simplifies this. This is the power set for X, Y, and Z, partially ordered by the subset relation. So you can see how much more simple it's become. Okay, this is what this looks like. And in Hass diagram form, it's this, so much simpler. The reason why is because in mathematics and more advanced studies, these, in terms of the study of relations, these become cumbersome. So that's one way of just simplifying them. So what do we have here? Let A be the set 1, 2, 3, 9, 18. And for any A, B, this element of A is precedes or equal to B if and only if A divides B. Draw the Hass diagram of this relation. So we can do that. Oh, we can, can't we? Well, it doesn't look like I've got it. Oh, there it is. It's just what we just did. It's just what we did. Okay. I mean, is it not just the same thing as this right here? 1, 2, 4, 12. 1, 2, 3, 4, 12. 1, don't know. It's not, but it's essentially the same project. Doing it all over again. I should have done it for you, but good enough. So class Y equals, we've already done this, okay? This is the most obvious equivalence relation, making it reflexive, symmetric, and transitive, yes. However, it is clearly also antisymmetric, making it a partial order as well. That's interesting. This is often not mentioned in textbooks since partial orders are rarely antisymmetric as well as symmetric. So they can satisfy both of these. You can look here to Math Exchange for that very interesting tidbit. Now, finally, chapter 3, which we bypassed, where your book has functions, but then good books, better books like Grimaldi, which we're not using, this belongs in the section on relations. Excuse me. In fact, I'm sort of I'm very exhausted right now. I've had a long day. If you don't mind, I'll just finish this off, and I'll post this right now, and I'll make the conclusion to this. We're almost there. See, we're halfway through. I'll spend another, hour and a half or so filling this out for next week, okay? And so I'll post it probably, because I'm sure none of you are looking at this during this part of the course because you're studying for the midterm. So there's no need for me to rush through this, but since this covers both weeks 9 and 10, I'll finish this off next week. All right? If you don't mind, I'm just a little exhausted right now. So see you in the next 10, I guess I'll call it 10, week 10. All right. Good luck on Monday. Please, please. You're not looking at this, I know. You're looking at this after you've written the midterm, but I hope you did well.